Okay, so today's lecture we will continue on RLC circuit transients, and if we have time we will start partial fraction expansion. Let me write this. This week 26, Monday. The readings from page 99 to 104. Then in Wednesday 28th, the readings from page 104 to 106, and also it's the due date for homework number 7. Then on Friday there is no class, last week, so there is no class, so you can have a spring break on Wednesday. Then the spring break from 3rd March to the first week of March. So spring break, no classes. Okay. Some important tables. These two tables of Laplace transformation, table 3.1, 3.2, those are in page 96 and 97. So we mentioned them a lot, and we also focusing on them because we will use them in our analysis. Before starting the partial fraction of the RLC transient, we already discussed it last lecture. There is just a notice from the TA about homework number 7. Notice. TA about homework 6. Homework 6. So the TA says that problem 3.5c, only 3 students got it right, while the rest of the class didn't have a problem with it. So I would like to explain how to answer this, because this is very important. So basically we need to find the Laplace transformation x of 3 equal 10 e power negative 3t u of t minus 4. That's our whole idea. How to find Laplace transformation? So basically we can say we have a time shift and u of t. But what matters was the concern inside the brackets u of t minus 4. Here we have only 3t. That makes a problem. So we cannot apply Laplace transformation direct. We need to make sure we replace every t by t minus 4. So we can make sure we can try to make t minus 4 here. How to put t minus 4 in this part, then if we can figure it out, we can probably do that. So how to do that? Basically, we can say t e power negative 3t u of t minus 4, then multiply by e power negative 12 times e power positive 12. How did I get this 12? Basically, I can say 4 and 3. 4 times 3 equals 12. Okay, what's the point of using this? We can say it will be 10 e power negative 3t, and we can say, put the brackets, t minus 4, because 3 times 4 will be 12, then times u of t minus 4 e power negative 12. So we just put the 12 inside the expression. So as a result, it can be as put the 10 e power negative 12 times e power negative 3 t minus 4 u of t minus 4. That's it. If you want to simplify, you find 10 e power negative 12. You can, or if you want to keep it, it's up to you. So it can be 6.1 times 10 power negative 5 equal negative 3 t minus 4 u of t minus 4. Or you can keep it in the other one as 10 power negative 12. Either ways are correct. Now I'm ready to do the Laplace transformation. So the Laplace transformation of x3 of t. This is equivalent to x3 of s, which will be, the constant will remain as s10 e power negative 12 or 6.1, whatever you want to call it. Laplace transformation of e power negative 3 times t minus 4, u of t minus 4. Now recall from the table, like e power negative at u of t equivalent to 1 over s plus 8. And recall that whenever we have a shift t minus 4, this is equivalent to a shift t minus t upper. This is equivalent to the e power negative ts. Now we have two properties can be applied here, which is a is equal to 3 and t uppercase equal to 4. So as a result, it will be as 10 e power negative 12, then e power negative 3t will be 1 over s plus 3, then further the shift, which is e power negative 4s. So you can keep it like this, or you can just say it's 10 e power negative 12, e power negative 4s over s plus 3, or if you want to say it is 10 e power negative 4 s plus 3 over s plus 3. You can stop at any point. Then that's it. Any question? Okay, so it's very important to understand how to do this problem, which is the trick, which is we have to apply two properties. There is a shift, and there is also the exponential form. Keep in mind, we cannot apply direct way this because the existence of t minus 4, and this is t. If there is not t minus 4, we cannot do this. Then we just did a trick to make it t minus 4. Now, let's go back to our topic, which is RLC transient. That's what we discussed last lecture. So last lecture we said it's RLC transient, therefore two storage elements, then it's second order. Then this is how the circuit look like, and I mentioned that VO and the switch, or the voltage source and the switch, can be replaced by a source with U of t, like this one. So the switch can act as U of t because the switch will be open at t equals 0. Then this is actually the definition of U of t. Now, we need to calculate the currents. How to calculate the currents? We will do KVL in this loop 1. By doing KVL at this loop, start from the left bottom corner, then from the clockwise, which will be negative V source plus VR plus VC plus VL equal to 0. Or in other words, V source will be VR equal to VR, VC plus VC plus VL. Now, what's the value of each one? Let's find the corresponding value of each one. V source is given in the question as V source of t given in the question as VO times U of t. That's given in the question. So this is VO times U of t. VO times U of t. Now, how about the resistor? VR, what's the relationship? Ohm's law, right? I times R. While VRT will be R times I of t, which is Ohm's law. Now, how about the capacitor? DC of t. What do we know about the capacitor? Is there any relationship between the current and the voltage of the capacitor? Yes, we know I equals C dV by dt, right? We know this from circuit analysis, that I capacitor equals C dV of the capacitor by dt. Is this correct? Now my target is to find VC, not IC. So we can say that dt, or just multiply maybe the products, IC of t dt equals to C dVC of t. Then let's do the integral. By doing the integral for both sides, we need to find the voltage. So we can say, let's put C at the other side. Then the integral for VC of t will be as I got it, say like this one, C of 0 to t, IC of t dt equal to the integral from 0 to t dVC of t. So this integral, it will equal to VC of t minus VC of 0. And in order to make it great, so we can say that VC of t equals to 1 over C from 0 to t IC of t dt plus VC of 0. That's, I just moved VC of 0 to the other side. In other words, sometimes we would prefer to use t and t like this way. So we will put a dummy variable. I'm going to put this out, and this one will be moved. Just the point is, for the integral, we would prefer to use the as t and t, so we'll make it as tau. And that's it. This is VC. So there is an initial condition, VC of 0. Then what else? Vs, Vr, Vc, then we have Vl. How to find Vl? The relationship L di by dt, right? That's what we know from circuit analysis. Vl of t equals L di of t by dt. Is this correct? Now I know the equations for these 1, 2, 3, 4 elements. VL, VC, VR, and V source. Let's substitute them. Substitute them in one equation. Again, we know Vs of t equals Vr of t plus 1 over C, plus Vc of t plus Vl of t. We will substitute them. With this will yields to be Vs, we know it as Vo U of t equals Vr, which is R I of t, plus Vc, which is we calculated as 1 over C, the integral from 0 to t, I of tau d tau, plus Vc of 0. Then the last one, which is Vl, will be L, the I of t by. Okay? So by looking at this differential equation, we have integral, we have derivative. So to remove the integral, we can do the derivative. So therefore, the answer or the overall differential equation will be second order. How can we solve this? You can apply the differential equation to these. Or we have Laplace transformation. So let's take the advantages of using Laplace transformation. So we'll use solve second order differential equation using Laplace transformation. Now we need to do Laplace transformation for every term. Let me label this as term number 1, this is as term number 2, term number 3, term number 4. So I'm going to do Laplace for every term alone, then I will group them in one equation. So let's start from term number 1. We need to do Laplace transformation of VO. This Laplace transformation, any constant, VO is a constant, times U of t. So it will be the constant itself. What's the U of t? 1 over s. So VO over s. Okay? We know the Laplace transformation. And you can also use the tables, assuming the tables that are available. Then the second thing, we need to do the Laplace transformation of R I of t. The constant R will remain as is. I of t will be I of s, right? So I of s. How about the third one? Third one, we need to do the Laplace transformation of 1 over C, the integral from 0 to t, I of tau, d tau, plus Vc of 0. Now, how to do the Laplace transformation? For this part, the first thing, 1 over C will remain as is. The Laplace transformation of the integral is 1 over s. So it will be times 1 over S times, then I of t will be I of S. Okay? So basically, we just say the integral is 1 of S. Integral, it is 1 over S, and that's it. That's the nice property of the Laplace transformation. Then, the next element, which is VC of 0. VC of 0, most likely it is like VC of 0, since it's causal system times U of t. Then it's going to be as VC of 0 divided by S. Okay? Then the overall answer will be 1 over C I of S over S plus VC of 0 over S. If we call here, VC of 0 is a constant, while I of S is a function that we don't replace, and we need to calculate. Then the only element left, which is number 4. Number 4, which is the Laplace transformation of I of t. L di of t by dt, which is the inductor. So basically, how can we do it? L will remain as is, because it's constant. Then what's the Laplace transformation of the derivative? Let's go to the table. So for the integral, we see that there's 1 over S. For the derivative, S, x of S minus x of 0. That's what we will do. So let's go back to here. It will be the derivative, which is S. Instead of x of S, we will say I of S, minus x of 0, which is, in other words, I of 0. Okay? That's it. So look for the initial condition I of 0. Now let's group them in one equation. Group them in one equation. So number 1 was VO over S. VO over S equals to number 2, which is R times I of S, plus number 3, which was 1 over C I of S over S, plus VC of 0 negative over S, plus number 4, which is L S I of S minus I of 0 negative. Okay? Then let's try to put the terms I of S on one side and the other terms on the other side. So basically, we have the terms that they don't include I of S, which is this one and this term. We will put it outside of the other side. So we want to split I of S alone. So basically, by isolating them, we will have VO over S. Then put this on the other side, it will be negative. VC of 0 negative over S. Then L times minus IO, negative L IO, I of 0. Then put it on the other side, it will be positive. So plus I of 0 negative times L. Then equals to what? I'm going to sum I of S and put I of S together. I of S. Then here remains R plus 1 over SC plus SL. That's the function. Then we will say, let's calculate I of S. I of S, that's what we need to do to calculate. It will be VO minus VC of 0 over S plus L I of 0 negative divided by R plus 1 over SC plus SL. Okay? Now let's multiply by S over S. Both sides. So this yields to be VO minus VL, or VC actually, VC of 0, negative, plus SL, I of 0 negative, over, here when we multiply by S, it will be as SR plus 1 over C plus S squared L. Or in other words, let's glue it together or make it more organized. It will be VL minus VC of 0 negative plus SL I of 0 negative divided by S squared L plus SR plus 1 over C. Okay? That's I of S. Now, I'm ready to substitute the values. Given in the question that VO is equal 1.6, VC of 0 negative given as 0.4, I0 of negative given as 0, then L was given as 0.4 Henry, then R given as 4 ohms, C as 0.1 microfarad, or no, it's 0.1 farad. Now let's substitute this value. So this yields to be VO 1.6 minus VC of 0, which is 0.4, plus S times L, 0.4 times 0, divided by S squared times 0.4, plus S times 4, plus 1 over 0.4. Then, let's do more simplification. 1.6 minus 0.4, this is equal to 1.2, plus S times 0, 0, then only constant, divided by 0.4 S squared plus 4S plus 10. Now, most likely, we prefer to make the coefficient of the higher order 1. So we will divide by 0.4, divide by 0.4 each side, because we want to make the coefficient 1. So by dividing by 0.4, this yields to be 3 over S squared plus 10S plus 25. This is I of S. So this format, I of S, this is the current, but it's in Laplace domain. Now my target is to convert this from Laplace domain to time domain. How can I convert this to time domain? One of the assumptions that we can say, this is actually can be written as S plus 5 all squared. So we can say I of S equals to 3 over S plus 5 all squared. So such that if we need to put the poles will be 2 repeated and negative. There are no zeros. So anyway, now this is the function I of S, and now the target is to compute, find Laplace transform inverse, or the inverse of Laplace transform. Sometimes put ILT, inverse. So that's why we need it, because we need to compute I of t from Ix. How to do Laplace transform inverse? That's one complicated thing. So actually, Laplace transform inverse, we will apply the following form. To find x of t, it will be 1 over 2 pi times j, we call j is square root of negative 1. Then the integral between sigma minus j infinity over sigma plus j infinity x of s e power st es. What's sigma plus j infinity? Most likely, we know that S equals sigma plus j omega. Here just will assume omega goes to infinity while sigma remains. Sometimes positive, sometimes negative. Then, after applying this formula, we can get x of t. But the concern is, this integral is not easy. So I would say hard to do, hard. It's not easy to do this integral. Okay, how can I know the Laplace transform if it's not easy to do this with the use the table. So basically, what we will do, use Laplace transform table 3.2, 3.1, 3.1. So we will do the inverse by comparing the table. You don't need to do the integration. How to use the table, which is the tables in page 96 to 97. Let's look here about the problem. So we need to calculate Laplace inverse of it was 3 over s plus 5 l squared. How to convert this? Laplace inverse. Let's go to the table and see. This table, look at something that has a square in the numerator, and where is it? Here. This is item 6. So 1 over s plus a squared equals t power negative at u of t. So what do we have in our analysis? We have 3 over s plus 5 squared. So we can say here a equal to 5, and the 3 is a constant, right? So it will be as, in this part, it will be 5 will remain, then t power negative, the constant 3 remains, t power negative 5 t u. Is this correct? Yes. So let's go substitute it. Then it will be as here, this is I and which is as I mentioned 3 times t equal negative 5t u. Then overall, you will say I of t equal to this one, 3t equal negative 5t u of t amperes. That's it. Then that's how we solve the transient RLC circuits using this approach. Okay, does this make sense? Now, if this circuit has parallel elements of series, and we need to calculate the voltage, the same technique, but overall we need to find the general equation. So with this example, the general equation that we did is the KVL. Then we substitute. If we have RLC as parallel, you will do the general equation as KCL and so on. So you need to find the equation that's make all of the equation in terms of one unknown, which is I of s, like what I did here. Then I of s will be like this transfer function or this Laplace linear. Then after that, substitute the values to get I of s, then make Laplace inverse. Then again, the same thing if you have, for example, a source, resistor, capacitor, inductor, and your target is to calculate, and I would say like isotope. Current source, and your target is the switch as well. Your target is calculate the voltage here. How to do it? Basically, you will do KCL. You will say this is IR, IC, IL, and here is I source, U of T, something like that. Pretty complicated. So you can try this. Try that one. So basically, you need to do the general equation will be KCL. So KCL will be as IS U of T equals to IR plus IC plus IL. Then you need to use Ohm's law for that one. So you find the equation, then do Laplace inverse. Then the overall idea is to find V of S equal to something, then find V of T. Okay? And regarding to the values of RLC and the initial condition, you can use the previous example values. Okay, so I want you to practice and how to use the transients RLC in your analysis. Any question? Now, one of the concerns is, will we do Laplace inverse? Here, we did a transition from this to this because we realized this one will be s plus 5 all squared, right? But it's not happening every time. What do I mean? Sometimes you can have an expression like, for example, 5 over s squared plus 2s plus 3, something like that. So how can I make a Laplace inverse with this expression? Let's assume that someone we can figure out to be s plus a times s plus b. How can I convert this into Laplace inverse? That's something that make it harder. So even go to the table, you cannot find this one. I mean, we were lucky in the previous example because it was over s plus 5 all squared, the previous example. So because of the square, we were lucky by finding this in the table. But not every time we will be lucky like this. How can I do Laplace inverse with this solution? Or how about if maybe the transfer function or the function can be higher order? So this is a new topic to do inverse, Laplace inverse Laplace transform. But we will use a method that's called partial fraction expansion. In other words, PF. So the overall idea of a partial fraction expansion is to convert this function that we have to a set or into a group of equations or a group of terms. Those terms can be easy to be calculated or can be easy to be converted to be Laplace transform to something similar to the table that we have. So our target is to convert this function into something similar. So for example, as I mentioned about 5 over s squared plus 2s plus 3, our target is to convert this to be something like k1 over s plus a plus k2 over s plus b. That's my target. Then I can use Laplace transformation domain, so this will be k1 e power negative at u of t plus k2 e power negative b t u of t. So if I can find a way to convert this into these terms, then Laplace will be inverse. Laplace inverse will be easy. This is for small. How about if we had higher order? So basically, now we will make a general rule, not only for having second order, how about third or fourth order, other order. So in order to make a general rule, I'm going to assume x of s equal to the high denominator, high numerator. So I'm going to assume this as b m s m. So such that this is the coefficient m power m plus b m minus 1 s m minus 1. Then we will go lower with lower order until reaching b1 s1 plus b0 s power 1 plus b0 s power 0. And we know s power 0 equal to 1, so there is no need to write s power 0. So I'm going to think about this. Then, the other part, it will be as an s power n plus an minus 1 s power n minus 1 plus, we will keep decreasing until reaching a1 s power 1 plus a0 s power 0. And we know s power 0 equal to 1, then there is no need to write it. And even s power 1 equal to s, so there is no need to write power 1. So until starting. Then, my target is, let me do first partial fraction expansion. Then after that, after doing partial fraction expansion, then we can do the Laplace inverse. So how to do the partial fraction expansion? I think maybe in the differential equation course, did you take partial fraction expansion in the differential equation course? equals to. Okay, so you're almost like familiar with this, but now let's gonna assume that if you have, remind you, or if you have no idea how to deal with this, let's try to do some definitions. Then after that we'll do some examples. So the definitions might look maybe weird, but with more examples we'll make it much easier. So we see that the order of the denominator and the order of the numerators are different. So we have m, we have n. Then, how to do that? Basically, look at the order m and n. M and n. So we have cases. So you have the first case, if m less than n, then x of s is called strictly proper. Strictly proper. Strictly proper. In other words, SP. So what does this mean, or how can we use this? Basically, we can say that, as an example, if we have S over S squared plus 1. So you will see that S squared plus 1, the order here, m equal 2, n equal 1, so m larger than n. Therefore, this function is strictly proper. Okay? The other definition that you need to know, if m equal to n, then x of s is called biproper. Biproper. Or b. As an example, when you have like s squared plus 1 over s squared plus 4, so here m equal 2, m equal 2. Okay? Then, number 3, when we have m larger than n, then x of s is called, I think, improper. X of s is called improper. As an example, when we have s cubic plus 1 over s squared plus 9. So we can say that n equal 3, m equal 2, so m less than. Okay? Now, you agree with me that we have 3 cases: strictly proper, improper, or we have the last thing, which is biproper. Now, how to do partial expansion? The first step is...
Professor Mahal.
Yes.
At the top of that, add at the top and add on the bottom.
Oh, okay. Thank you for this. And sorry for this. So here and I'm gonna just fix this. Thank you. So please make sure to fix this in the notes. Okay. Now, how to deal with this problem? So the first thing, make sure all the function, all elements of the function, or the function, make sure the function is strictly proper, which is make sure that n larger than. Again, as an example, like s over s squared plus 1. Okay, not every function is strictly proper. What should I do? If the function is either improper, or biproper, like what? When n less than or equal to m, as an example, s squared plus 4 over s squared plus 1, or s cubic plus 1 over s squared plus 9, something like that. What we need to do, then convert it to be as, like whenever we have like x of s, it will be as, and then I can call it as r of s plus function. I can call it as this one. So we have x of s is n of s over b of s. Then it will be as residual a of s divided by b of s c of s. So we'll convert it like this way, such that this way will be strictly proper. What does this mean, and how can we convert it? Basically, we will try to convert, for example, s squared plus 4 or s squared plus 1 to be a constant plus something over s squared plus 1 plus something, such that this constant, I can call another constant as constant here. This one is written as strictly proper product, which is this part is strictly proper. That's my target, is to get part of it as strictly proper. How about if I have like s cubic plus 4 over s squared plus 9, it will be as a function k1 plus k2 plus over s squared plus 9, and I say k3. Okay, how can we get this? Or how can I know it will be k1, k2, k3? You don't need to memorize this. Basically, the conversion can be done using the long division. Conversion can be done using the long division. This means, in other words, whenever you have improper or biproper, use long division lenses as a rule. Okay, how can we use the long division? Let's see an example to get a clear image. Example. X of s is 2s squared plus 8s plus 6 over s squared plus 2s plus 1. Now this one is here, m equal to n equal to. Therefore, m equal n, then it is biproper, which is 2. Therefore, let's use long division. How to use the long division? Make a lens. Here is s squared plus 2s plus 1. This is 2s squared plus 8s plus 6. Then start from the higher order and the higher order here. I think I messed it up. It should be the denominator. So here, 2s squared plus 8s plus 6. That part is the denominator, which is s squared plus 2s plus 1. Now the higher order is 2s squared, and the highest order of the other part, 2s squared. 2s squared divided by s squared, 2, right? Here's 2. Now, you can say 2 multiplies all of the terms. 2 times s squared, 2s squared. Then 2 times 2s, 4s, right? Then 2 times 1, 2. Let's do subtraction. 2s minus 2s, they will cancel each other. 8s minus 4s, this will be 4s. 6 minus 2, 4. Right? Now, 4s and s squared. 4s is lower order than s squared. Then stop. Because 4s lower order than s squared. So the overall result x of s can be rewritten as, since it can be rewritten to be the 2 plus 4s plus 4 over s plus 2s plus 1 squared s plus 1. Okay? Do you agree with me? That's how we convert this. Now it's strictly proper. We can do some simplifications. Can be like 2 plus, put 4 as a factor, s plus 1, and this s squared plus 2s plus 1, which will make it s plus 1 all squared. This one will cancel each other. Then the remaining will be 2 plus 4 over s plus 1. This is x of s. Now, can you do Laplace transformation, Laplace inverse with this one? Yes, we can. So Laplace inverse of x of s. What's the Laplace inverse of a constant? Delta 2 delta 2. What's the Laplace inverse? Is a constant form. S over 1 over s plus 1 e power negative t u. This is x. So it's very important whenever you do the partial fraction, you must first thing do the log division to make sure everything is be strictly proper. After being strictly proper, now we are ready for the next step. Is either we can simplify the two Laplace transformation, or we can do the long or the partial fraction. This is still not partial fraction yet, but this is one process in how to do the long division. So next lecture, I'm going to continue more on log division and also do some partial fractions. So let's start with this.